Hello friends, welcome to my YouTube channel. So we are going to start measure theory. So there will be series of lectures on this, and this is our first lecture in which we are going to see what is algebra of sets. Okay, so first of all, as the name suggests us, the measure theory, that we are going to measure something, right? Like if we have a set X, then what we can measure is the cardinality of set X. Okay, if we have an interval in real number, then what can we measure is the length of that interval, right? That length is b minus a. So we are going to measure the different things. So in this is our lecture number 1. So in this we are going to discuss algebra of set. What is algebra of set? So let's see the definition. So what definition says that let X be a non-empty set, then a set C, which is collection of subsets of set X, is said to be algebra of X if the first condition is if some set A, that is subset of set X, belongs to C, then A complement belongs to C. Okay. So if A is subset of X and A belongs to C, then A complement also belongs to C. Another thing is if both A and B are subset of set X and they belongs to set C, then A union B should also be there in set C. Okay, so this is our definition of algebra of sets. Now we will see some trivial example of algebra of sets. So what are some trivial examples? First example is the set phi and x, which we call C, is itself an algebra on X. Why? Because using our definition that if A belongs to C, then A complement should be there. So we know if phi is there, then its complement X is already there, right? And vice versa. Also, if A and B belongs to C, then A union B belongs to C. So the union of phi and X is X and it belongs to C. So therefore it satisfies the condition. The second trivial example is power set of X. Power set of X, which is collection of all the subset of X, right? So if I have a set A which is subset of X, and obviously A belongs to power set of X, also A complement is subset of X, so A complement also belongs to power set of X, right? Second condition is if A and B are subset of X, then A, B both belongs to power set of X. Okay, and if A and B are subset of X, then A union B is also subset of X, right? So A union B also belongs to power set of X. So these are some trivial example of algebra of set X, right? So now we are going to discuss some properties of algebra of sets. Okay, so some properties. First property is if S1, S2 to Sn belongs to algebra of set X. Okay, so let's define C is algebra of set X. Okay, so let S1 to Sn belongs to C, where Si's are subset of X for all I, then S1 union Sn also belongs to C. Okay, so it's very easy to check because we have to check only two conditions. A condition was that if A belongs to there in the union S1 union Sn, then what happens? We know A belongs to Si for some I belongs to 1 to n, right? If that happen, then obviously A complement will also be there, right? Why? Because all S1 to Sn belongs to algebra of set X. So their complement will also be there, right? Therefore, A complement belongs to Si. Same thing we can prove that A and B belongs to union, then our A union B will also belongs to this union. Okay, so now let's see another example, that if S1 to Sn belongs to C, then S1 intersection Sn belongs to C. Okay, this thing is also clear. Why? Because we can easily see that if A belongs to there in the intersection, then A belongs to Si for all I, right? I belongs to 1 to n, right? That's why it will be an intersection, right? So A complement belongs to intersection Si for I running from 1 to n. Okay, why? Because all the Si belongs to C, right? That was also the trivial thing. So these are some properties of algebra of sets. So that was all for the today. Thank you for watching. Hope you understand this.